Imagine trying to weigh 3 rolling objects, a bowling ball, a baseball, and a ping pong ball, without using a scale. If you roll them across a table and hit them with a strong gust of wind, the ping pong ball is blown off course, the baseball curves slightly, and the bowling ball plows straight ahead. To find the mass of a single molecule, chemists use this same physical principle. We don't place the sample on a scale, we launch it at high speeds and try to blow it off course. Today, we are going to determine the precise mass of a single molecule of neopentane. Mass spectrometry converts the mass of a chemical into a measurable physical trajectory. This diagram outlines the 5 sequential stages of the instrument: the sample inlet, ion source, mass analyzer, detector, and readout. Notice the vacuum system connected to the center of the machine. The ion source and mass analyzer must operate under an extreme high vacuum. If the chamber contained normal air, our vaporized neopentane molecules would crash into atmospheric oxygen or nitrogen. They would scatter long before reaching the detector. To track a molecule through these 5 stages, we have to look at the sample through the lens of physics rather than chemistry. This schematic shows the ionization chamber. After neopentane is vaporized, it is subjected to a violent bombardment by an electron beam. The collision knocks a single electron off the molecule, leaving a positively charged molecular ion that retains the exact mass of the original neopentane. But this electron impact is so harsh that it causes many of the neopentane molecules to structurally shatter into smaller pieces. We now have a chaotic accelerating cloud in the chamber, a mixture of intact heavy ions and smaller shattered fragments, all carrying a +1 charge. The ions accelerate into a curved vacuum tube surrounded by an electromagnet. The magnetic field pulls them. Lighter fragments crash into the inner wall. Heavier ions hit the outer wall. Only ions with 1 exact mass-to-charge ratio carve the perfect arc to slip through the exit slit. As we sweep the magnet's strength up and down, the detector counts the hits of different masses as they pass through that slit. Because the charge of the ions is almost always exactly +1, sorting them by their mass-to-charge ratio is effectively sorting them by their exact molecular weight. This chart shows the final readout, the mass spectrum of neopentane generated by the detector. We see scattered peaks at m/z 27, 29, and 41, a massive peak at 57, and a much smaller peak resting at 72. Take a moment to pause the video here. Based on the difference between shattered fragments and the intact molecule, which peak represents neopentane's true weight, and what is that huge peak at 57? The machine only provides the raw wreckage. The human analyst must know how to reconstruct the crash. The answer is the peak furthest right. This peak at 72 is the intact molecular ion, proving neopentane's weight is 72. The tallest peak at 57 is the base peak, representing the most abundant shattered fragment, not the total weight. This spectrum serves as a structural fingerprint, revealing the specific ways a molecule breaks apart under stress. Let's recap. We vaporize the sample in a vacuum, then ionize it to create the parent ion and its fragments. Then we accelerate the ions, deflect them by mass using a magnetic field, and count them at the detector. By tracking these high-speed physical trajectories, mass spectrometry calculates the exact mass of individual molecules.